Okay, so our final speaker this afternoon is Kurt Schwehr from the University of New Hampshire. And Kurt's a proper techie geek, so it's fitting we end with one. But he's involved in using his skills in a number of areas in planetary, but in particular ocean data. And it's that he's going to be talking about today, how he's developed uses of geospatial data in Google's Geo tools.
All right, thank you. I want to start off with a figure to remind you all that New Hampshire indeed does have a coastline. We have 17 miles of coast, and we actually do touch the ocean. Most people don't seem to realize that. And I'd also like to acknowledge my collaborators. Many people at NOAA, Cornell University, and the U.S. Coast Guard have contributed to the products you'll see up here today. And I want to go back into the not too distant past and talk a little bit about where we used to be before we had Google Earth and some more tools. When we were at NASA, we used to have to spend huge amounts of money trying to buy large SGIs, keep them running, and then write all of our software on our own just to make this crummy looking Earth that's up here. And there's no nice textured background. It sort of looks like North America, and we sort of have a red blob on there, and if you click on it, it pops up an actually fairly nice graphic of something, but there's no way to scale in between the two and handle all the nice things that Google Earth now handles for us for pretty much for free here with KML. And you used to have to get a van and truck it all over to where you're going to do your demo, and today we take our laptop, open it up, and you're good to go. That's had a dramatic effect on how we've looked at data and how much data we can look at. And I'd like to take a little bit of a tour where we went and what kinds of things we're trying to do to support the mariners who are out there on our waterways trying to get commerce through and to keep our economy running. And my background is a little bit of geology, so I want to show you sort of how I got into Google Earth and what we started looking at first. So here's the Santa Barbara Basin off of California, and we started looking at what we could do with, say, taking a journal paper and scanning the figures in, or using something like Fledermaus to generate a 3D model and then slap it in there, or actually just texture your bathymetry onto the ocean floor when we have a high-resolution survey. In this case, it's from Mbari's research ship. And as you go through that, I started playing with the idea of taking each scientist and maybe we could build a Google Earth resume. So it's a concept of, for a particular scientist, where they've been as they go through their career. And you can actually glean a lot as they go through the geologic record trying to figure out what's going on. A lot of insight comes from what problems they're looking at and when in their career and how that influences things. If you went back a ways, you might see the revolution that occurred in earth sciences where people realized that plate tectonics is a real thing. It was a huge change of thought to people, and a lot of that is buried in the literature in terms of where they were looking on the ocean and how they looked at the Earth. They went from an old model to a brand new model that was really radical change. And so I think as we dig back into those archives, we'll start pulling out more of that and really see a historical change. Now, to jump into some of our modern tools that we're looking at and give you a sense of what we can actually do for the mariners to change their world and make it a better place for them to move about on the waterways and for those who are managing it. I used an open source tool just to get going, and we took a NOAA chart, which are the little red lines you'll see up on the screen. And on that chart, we've dropped it on top of Google Earth. And if you look at the pier in the middle next to the orange arrow, you'll see a really long pier next to a really short red icon, little iconographic description of the pier. Now, which one is right? If you came through in the middle of the night, do you want to find out? So we've been looking at if you could just drop a chart in and do a quick look, you can catch a lot of errors that have been very difficult to see down the road. And I'll show a couple more examples of kinds of surprising things that we've found and how tools like Google Earth can just pop this right out without having to go through and dig through databases and try to look at Excel spreadsheets and figure out what's going on. Now, as these ships move around, there's actually a new technology that's been deployed for about the last 5 years and is coming into more and more use, and it's called the Automatic Identification System. So planes for a long time have had devices that tell you where they are, and the FAA can tell you what ship is where in the United States. Well, now we have that for the maritime world. So ships are starting to put these transponders on, and they're mainly meant for collision avoidance. So instead of just having to rely on your radar, you have a device that actually tells you who's around you and what they're doing. Now for us as researchers, we'd like to see what are the ships doing, why are they out there, why are there problems, where are there areas that are working well. And so what you see up here is a combination of a little bit fancier nautical chart. Here I've used the Earth and Sea charts, and I've taken a couple layers out of their tools and merged it with AIS ship tracks throughout entry to Delaware Bay. And you can see that there's vessels moving all over. Some are using the green traffic lanes and following the rules of the road. They're not required to, and there's other vessels who are crossing it. And then there's vessels that have to wait around for some reason. And so we need to go in there and look at, as they're out there, what's delaying these ships, and how can we optimize what they're doing while keeping them safe. Now, it's not always safe out there, and things do happen. So we can use techniques like this to look at events like the Cosco Busan. This ship in 2007 ran into, or as they call it in the maritime world, alighted with a fixed object called the San Francisco Bay Bridge. And by having the ship track in and recorded by all the transponders, we can see what was going on with that. And the investigators, I'm not involved in that, but they can actually look at these tracks and start to understand what's going on. And we can provide them with graphics where they can go in with a time slider, move things around. They can remove all the ships except for the ships that they care about and start really digging into why this incident happened. And hopefully with those investigations, they can create new rules or remove rules that were causing problems to make the waterways more effective and safe. And you can combine that kind of information with things like in the bottom left, we have an image that was captured by the ship's radar. And so investigators can really get a fuller picture of maritime incidents as they happen in the waterways much better than they ever have in the past. Now, as a part of that, in addition to things like AIS, we also need to get more sensors out there. NOAA, the EPA, and other federal agencies have got a pretty good infrastructure out there, but we need more. We need sensors that really go in and tell us what's going on in the environment. So here I've shown an example of a company that's trying to push that innovation curve, SensorWare Systems, and they're trying to place all sorts of sensors out in the environment and give us tools to be able to go in and look at this stuff 24/7, 365, good days or bad days, and tell us what's going on out in the environment. That way, we as scientists and researchers can really understand what it is that's causing those trouble spots and why things are working the way they are in the waterways. If you don't know what's happening out there, how are we supposed to help them out? Now, one of the things that we try to do is once you have an incident, there's a short time period where responders have to get in there and really start to work with the local enforcement folks and try to get that environment cleaned up and restored back to where it was. So to give you an example of some of the things that we're seeing in the waterway, I've shown you a picture of a grounding in Alaska. This could be anywhere in the United States. There's a lot of incidents on the waterways. It's getting busier out there, so things do happen. It's like being on the highway. You don't expect to have an accident, but every once in a while, something happens that it may even be out of your control. So we've been working on web interfaces to provide a consistent environment for each of the ports to have that they can call up, and responders who come from out of town may have never been in this particular area. They need a consistent view of what's in the area, consistent set of data products, and access to the management plans that have been in place so that they can quickly respond to things such as oil spills, where every minute or hour that you can't get out there and figure out what to do causes you to not be able to recover as much of the oil or debris that's out in your waterways. So here, for example, we're showing multi-beam bathymetry, showing super high resolution features of the waterways. This is Portsmouth, New Hampshire. And you can see such things as sand waves that are just a meter or two across. And you combine that with your roads and highways, and the icons show you all of your caches for your response tools. This way, the people who come on site, they may not have been here before, but they can get going right away and start to figure out what they need to do in the first few hours of a response. Now, once you're way past that and you've gotten past your investigations, such as the Cosco Busan, the Coast Guard keeps a database of incident investigations. Part of that database sits inside of a tool called MISSILE, and it's the Marine Information for Safety and Law Enforcement database. And as a part of that, we have access to these incidents, and we can color code them. Here I've used the OSHA symbols for industrial accidents. Not quite the right icons, but it gives you a gist of what's going on in the waterways, and you can see what are the areas that are having the most trouble, and where do we need to focus our research efforts to make this a much more focused research and find those problems that need to be addressed. You can see that the Gulf Coast has the majority of the incidents with a fairly good number going on in our inland waterways. So Most folks refer to themselves as the brown water crowd. They have plenty of incidents that they need to work on too. There's a lot of tight waterways and passing arrangements that are difficult with these big ships trying to move our economic resources up and down the Mississippi River. If we zoom in here, this is Norfolk, Virginia, and you can take a look at their database. We started to create tools that help associate these together without having to dig into their Oracle database, so anyone can go in and associate a particular incident with the details of the accident, or you can drill down and get the entire accident report. And that way we can start looking at what actually happened to an incident. Is there something we can address, or is this, say, an act of nature or a weird current, something that we can't control, therefore there's nothing we can do about it, or can we add a sensor to help ships out as they come into particular areas? An example of that might be the inland waterways. Some of the locks, as you approach them, have really horrible cross currents that vary with time. So can we put sensors in the water column that will tell you the currents and report that back to the ships? Now, as mariners go through the waterways, they're relying on groups such as NOAA to provide them with the resources to understand where they're going. This is the Road Atlas for ships, and it starts with field data entry. There's validation, and then NOAA produces what's called the Coast Pilot. This is a document that's been around for a very long time, over 100 years, and it hasn't changed in 100 years. So we have a really excellent tool. Mariners count on this, but can we do better with a geospatial tool? We took a look at LiDAR, and LiDAR is great. You can generate thousands of laser points ranged into your environment, and you can look into buildings, see trees, all sorts of stuff, but it generates a lot of data, and you're going to overwhelm your people who are trained mariners who are not used to dealing with point clouds with data that isn't necessarily going to help them. This might be helpful for a modeler, and we've looked into what we could do with producing models to supplement those that people like Google have created, and we can add the waterway critical buildings and markers. So here we've done a lighthouse on Cape Cod. This is Highland Light, modeled by Christiana. And in this model, it gives us a good sense of what's out there, but unfortunately, if we were to do all the lights and waterway devices that we want to have out there, it's prohibitively expensive and time-consuming to model each of these. It takes us going out to a site, running around the building, building a model, validating it, going through all of our tools, and then dropping it into SketchUp and placing it into Google Earth. The last two steps are easy. All that leads up to that is actually fairly challenging for these unusually shaped objects. It would be nice if all of our lighthouses were square, but unfortunately they're not. So we've looked at an approach of running around with a camera, and cameras are getting better every day. They're adding sensors that we need. It used to be that adding a GPS to a camera was difficult. Now you can go to the store and you can buy a camera that has a GPS and it has a 3-axis magnetic compass, so you know which way it's pointed. Another engineer and I, Matt, we went through Boston Harbor in one day and photo surveyed the entire harbor. We had very sore arms from trying to hold a camera stable on top of a ship. But you can go in one day and survey an entire harbor. Now, how can we use that information to present something to go along with that text to produce a new environment that's helpful for our mariners? So we've come up with a process. Collect a whole bunch of photos. So here's Matt and I collecting photos in Boston. You need to match those photos to features. You need to crop those photos, register them, orient them, and get them into a database. And once we have that, we can try to create interfaces to this new type of data. We've been playing with, as Matt calls it, the multi-rama, where basically you have an oriented image slice, and the renderer picks which one to do based on which way you're looking at it. The nice thing about this is, unlike a CAD model, you catch all those features that cue the mariner into what to look for. So if a building is buried among the trees, you capture all those trees that you would never want to model in a 3D world. It's just too expensive. So in our lab, we've gone ahead and prototyped a little version of this to see what it might be. You're welcome to download it and give it a try. We're always looking for feedback. We've got some features that we haven't figured out how to do in Google Earth yet. As you move around this world, you'll see pictures moving smaller and larger based on where they are in your field of view. Things are bigger in the center and they shrink as they go away. We've played with the aspect-oriented which picture to choose, and we've had hyperlinks between the text and the 3D world. We think with the new JavaScript API for Google Earth that might be a great way to create at least the basics of this and then work through how we're going to implement some of these other features on top of what exists in the current KML. I think we can do a lot, but we have yet to figure out what that might look like. There's a lot we can do, and we're going to try a few things in the next couple months, but we look forward to feedback on that first prototype to see what might be a good match for people without overloading the interface with too many things. Now I'd like to show you something in our actual in-the-field implementation of stuff. This is a project that's just going online right now. The Right Whale AIS project aims to notify mariners without any effort on their part of where right whales might be in critical habitats. The right whales on the East Coast, we're down to about 350 right whales. And so we'd like to give the mariners as much tools as possible to avoid running into these whales, or if it's impossible to know the whale's there, to at least be going slow enough that any impact with a whale might not be fast enough to actually harm the animal enough to kill it. So to give you a sense of what's going on in the Boston area, here's a figure to give you a view of a couple of different types of ships and how they use the waterway. Some ships, such as fishing or tugs or research vessels, they're the worst, don't really work in a very nice, easy to work with manner. However, that cargo and liquefied natural gas carriers tend to really run a very consistent line. They use the traffic lanes very consistently. And as a part of a new deep water port that's being put in here for LNG right off the coast, the Coast Guard, NOAA, and the local natural gas companies have agreed to spend money to put in buoys all along this to let mariners know when whales have been heard in a particular area. So let me show you the first implementation of this user interface for the mariners. We did it in Google Earth. It was the easiest tool to create an interface that we found. And what we have is a circle for each of our buoys. And when that buoy detects a right whale call, it goes back to mission control at Cornell University. They verify a whale, and the little ring on the screen turns yellow, letting the mariner know that there was a whale there sometime in the last 24 hours. This way, mariners can use their best judgment to understand what to do, or if you're the LNG carrier, you're actually required by your contract with the Coast Guard to go less than 10 knots. Now that we have those kinds of things in place, we also need to start working on our background data, and we've been looking at how to deal with multi-beam data with Google Earth so that we can have rapid turnaround of validation of our tools without having to deal with the multi-day process of processing with the high-powered tools such as Keras. Here's an example of a really unusual system and how easy it is to drop into Google Earth. I used a combination of MB system and Google Earth to drop in the track lines, make sure that this wave rider, which is a little jet ski-like device with a sonar on it, driven by Tom Lippman of our institution, to actually go in and quick make a model of this and see if we can go and make a nice model of the inshore areas where we can't get ships. So we're trying to work on new ways to acquire data and get it into Google Earth. Now, as we go through all this stuff, we're trying to deal with a whole bunch of research papers that are focused on various waterways and the bottom of the ocean, things like that. We have a request of Google. We would love to see, instead of just Google Scholar, Google Spatial Scholar. So we've actually done a quick prototype of what it might be to lay in the historic data. We had a whole team of graduate students who came up with this project, and they took old multi-beam data that were figures in papers and laid it on Google Earth where those figures should go. Now, maybe the end result, you really want these things glued right on the planet where they're supposed to be. But this shows the idea of being able to take a database such as EndNote and export a KML and be able to just spin around the globe and see where the papers are. So if you're interested in Hawaii, you fly into Hawaii and you just get the Hawaii papers. Now, I'd like to finish up with an example of a tool that's about to come online. It'll be a little bit longer than the whale system. This is NowCoast, done by NOAA. And they've worked with the University of New Hampshire to create a tool called FlowViz and get it on the web. This is an ArcIMS interface. So if you go to NowCoast, this will be there hopefully in the next month or two. And we've worked on visualization techniques that actually are based on the human visual system. So this sort of starry night view is the current velocities along the U.S. East Coast. You can see the Gulf Stream nice and clear. And as we're working on this, we thought, what if we did it in Google? What if it was right on the globe and we weren't always in ArcIMS? So we've taken a quick look at that, and it looks really promising. Here I used Flitermouse to go and drop a GeoTIFF onto Google Earth, and the results are really quite stunning. Being able to fly around and really see this kind of flow model is fantastic. This is something when I had to take oceanography as a grad student, I would have killed for this visualization. I still don't totally understand flow visualization. I'm not an oceanographer. I'm a marine geologist and geophysicist, but it's really great to be able to see this stuff and understand the context of my geology within the currents of the area. So thank you all for listening. If you have any more interest in this type stuff, my blog at schwehr.org has a lot more pictures of all this stuff, and you can download some of the files. Thank you for listening. Any questions? Yes.
I was just wondering, Google is something like Street View. Would that be moving to coastal feature?
Could you repeat the question?
Google is what? Street View, right? And then it's a specialized car or something you drive by and you basically stand everything together.
We would rather have Google do that than us, yes. It would be great to have a Street View car that we plunk on top of a ship and drive around a harbor. We're in a way emulating that, except for one aspect. In Street View, you want to show everything because people are interested in all sorts of different features. Here we have a community that actually wants you to go in and decimate the data and just find those key features. So when they're coming into a harbor, they don't want to know every nook and cranny of the harbor. They want to know the key lighthouses, the buildings, the features they need to go to where they're going. So they're going to aim for that lighthouse, take a left at the third pier, and head for home. And it may be foggy and dark, so they want to have that best knowledge without all of the Street View-like stuff in there. So we have an extra decimation problem. Yes, next question.
You had a slide up where this prototype that you're doing was it Coast View or?
Now Coast?
No, not Now Coast, farther back.
That one?
No, before the whales.
Before the whales.
You were taking photos and yes.
That one, yes.
This is Google Earth, right? And
This is not Google Earth. This is our in-house OpenGL implementation, and we hope to have a Google Earth implementation. We have a couple different teams taking their own take on it. We have one in Florida. We've looked at photo overlays, and we think that might be a way to go. We have some questions on how to control the image views to maybe do something like the multi-rama. We think you might be able to pull that out with sort of a level of detail region type feature where you pick which region and it's not true level of detail. So perhaps those kinds of things, but this is not currently Google Earth. I wish it was, but it's not. Any more questions? Thank you.